bit, but can you imagine it's opened now? We have Vivado. Congratulations. Have you guys figured out to install Vivado on your machine?
Yeah.
Everything smoothly okay? Everything's okay so far?
So far, so good, yeah.
So far, so good. Okay. So I'm going to show you something on Vivado. Then we'll return it back to the slide. Then we'll return it back to Vivado and so on. Okay. So let me share my screen. Now Vivado is here. Everybody can see Vivado, right?
Yeah.
Yeah.
Okay. So now we're going to start again. So create a project, right? Can you see the screen popped out? Create a new Vivado project.
Yeah.
Yes.
Okay, so we say next. They're gonna be week 2. We're gonna put it under the course, right? Because whatever code I will write, I will share it with you also. Okay.
Awesome.
So courses 3300. 2022. Let's put it there. Okay. Select. Next. You guys remember this, right? I already discussed this many times, right? So RTL, whatever. We're gonna select which one? RTL. Then we're gonna create sources, right? So leave it for now. Next. Basically, we choose your target language is what? Verilog. Are we gonna allow mixed languages or just like using Verilog? Keep it mixed, and I will tell you how. If we have time for by end of the course, I will show you how can you mix languages. Okay. Then next, then constraint. We don't have constraints. Then remember the XA7, right? XA7A100 TCS, and then -1. You remember this step or not?
Yeah.
Then next, then it says here everything is perfect, fine. I'm gonna say what create. Let's see.
Professor.
Yes, sir.
Just to clarify that last step where we clarified the part, what exactly is that for again?
The package. Do you remember when I said XC700 AT, right? And then I said CS whatever, right? CS, this is the package, the packaging, the type of package that the transistor is covered with.
Okay.
Okay, anyway, now it's open in front of us, right? Here, the target language, mixed, not defined, and so on, right? Correct?
Correct.
Hello?
Yeah, we hear you. Yeah.
Hello?
Yep.
Hello?
We can hear you.
Yeah, I think I have a problem with my headsets. Maybe there is a noise around the area, so it's whatever. Anyway, now we're gonna start our project. So if you guys remember, we said that the language, you have to have module, and then you have to have end module, and then from there you can define input and outputs ports, right? And there you can start defining the types of data that it will help you to write the code or whatever, right? And we said there is a different type of approaches for implementing any algorithm or any pieces on the Verilog. We said we can use git levels, or we can use a structure modeling, or we can use data flow modeling or behavior model. Do you guys remember that?
Yes.
So we're gonna start slowly, right? Which is git level, right? So here we're gonna say what add source. You have 3 different categories, right? You have constraint, you have create a design source, and you have simulation. If you guys remember from my slides, there was 2 different passes of simulation and design, right? One is the testing and simulation and verification, and one is for the design, right? We are not writing test bench. Test bench, it will be simulation. We are writing the Verilog that will be deployed on the chip. So that's why we're gonna select design. Other thing, we will need also to create the constraints. And the constraints will be the set of the input-output ports associated with the board that I'm sharing with you now on the screen, on my camera. You can see the board.
Yeah.
Yes.
Okay, perfect. So now we're gonna say create design source, and there we're gonna say create. Create what? Let's say create the first test, or whatever. Let's make it add what's called the full adder that we built last time on the Git level, right? Say here full adder, FA, right? And remember, this language is what? Case sensitive, right? So say here, okay. Then we say finish. The good thing about this language, I mean, the newer version of Vivado, the one I use in front of you is 2018. I didn't use the higher level. The higher level didn't work with us last time, if you remember. Because my laptop is the Microsoft Surface Pro 3. So it's not even meant for heavy computation stuff. So that's why, it didn't work. But anyway, here, Vivado since 2015 allow you to start writing the input-output ports. It will create it for you. So the question here, we are building a full adder, right? What are the input ports we have for full adder? Carry input, right? And the type of it, look, we have 3 different type of input and output and in and out. This is what the parameter-based input. So what is the type of input? You can have inputs, you can have output, or you can have input and output at the same time. They call it in-out. CN for the full adder is what? Input. Sounds good?
Yeah.
Now, is it single bit or a multiple bits? It's a single bit.
Single.
So single bits, I'm not gonna use bus. But imagine that it's a multiple bits. Then you're gonna choose what? Bus. And in that case, if you say bus, you can define how many bits from the left to the right, most significant or less significant. Let's say that I would like it to be 4-bit. I'm gonna write here what? 4, 3, because 3 to 0, 3 to 1, 0, 4-bit. But this is not the case, so I'm gonna remove it. It's a single bit.
I got a quick question. What does bus mean in this case?
Bus mean a bunch of wires. A set of wire having the same rule. So CN can be a wire or a set of wires. Right?
Both are okay. Single wire is not a bus, but multiple wires is a bus.
Yes. So CN can be 1-bit, or it can be 4-bit, or it can be n-bit. Right?
Right.
In our particular case now is what? 1-bit. So far so good?
Yeah.
Okay. Now the 2 operands that will be added to each other, right? We can call it port underscore A, and we can call this port underscore B, right? Sounds good?
Yeah.
Yes.
Okay, now I would like you also, while you are writing code, you have to understand something is called readability. What's called readability. What does readability mean? You make sure that your code will be what people can read it. It's not just you reading it. I can read it, somebody else can read it. Why this is important? Because in industry level, they look into the level of the industry level, they look into what? How you are writing code. So Microsoft, they have a booklet on internet you can buy, or even Amazon, about how they are naming their what? Wiring, variable signals, and so on. So let's act like them, right? First of all, if you would like to name a certain port, it's better for you to use in the beginning what? The name of the module. So what is the name of the module? FA, right? So far so good. So I'm gonna write what? FA underscore CN. So that means this CN is for what? FA. Then here FA port A. Then FA port B. Those are the three inputs. Do you guys agree?
Yeah.
Is there any other inputs going into this full adder? Huh? Are we gonna have any input to this full adder?
No, I don't think
Okay.
so.
So the output is gonna be what? C out. So FA port out, right? And this case, this direction is gonna be what? Output. Is this output single bit or multiple bits?
A single bit.
Single bit. So we go here and then, we do what? Enter. So we can have one more here and we just go here and say what? If A port out. There, we're gonna do the same thing. If A port C out. That means carry out, right? And that's also gonna be out. Is there anything else that, this block can have as input and output?
No.
No. Then we can say what? Okay. We will wait a little bit. If you can see the receive updating, right? Can you see this thing is going around like this, a circle?
Yeah.
That's generating what we already requested. And it stopped, right? So I can go here and I click on it. Have you noticed something? In front of FA, there is like a 3 dots in a triangle face, right?
Right.
That show you that, that's called what? Top module. So if we have a many of those and you are building them in each other, you have to choose a top module. Since we just have one file, they call it top module. Okay? Later on, we're going to complicate it. Sounds good?
Sounds good.
Now, when I click on it, the file is dot what?
.v.
.v. In the beginning, if you remember when we said how you make a comment, right? We can write here company Cal Poly Pomona. Engineer, you put your name. Design name, full adder. Project name using gates for building full adder. Device target is ECE3300, right? Tool version Vivado 2018.1. And description using Verilog as one of the hardware description language. Sounds good? Is there any dependencies? Are we building any other module? No. So basically there is no dependencies so far. We can use it later, we can write it, okay? What we built so far is called a module. What we built so far is called what? A module. That's why, have you noticed? It's called module FA. And then with the two parentheses here, it defines who's an input, who's an output based on the list that we already created. So far, so good?
Yeah.
Yes. Yep.
Okay. Something to tell you. I like actually to have what? Have you guys heard about an editor? It's called Sublime.
No.
Search for it. There's something it's called Sublime Editor. I already installed it in my computer and there is a correct version for it. I can give you the key. It's for the 3 version. And better than using the editor for Vivado, because I would like also to teach you some advanced techniques to use Vivado without graphical user interface. So I will try to teach you like, we are working for a company and we are having tests. Okay. Anyway, be sure The inputs are wires. The tools embedded this information I mentioned called wire, and it didn't write it to you. But in reality, it's a wire. So if I can write wire like this is the type of the thing. Is it gonna be wire, just passing something? Or we're gonna be storing, so it will help to store. If it helps to store, it will be REG, register. Sounds good? So any input is wire for us. But you know, we don't need to write it because the tool recognizes it. Sounds good? The output, since it's an output, so that means it might store or it might not store. Do you agree? In our case, the output is wire and is embedded as wire. But if I would like to change the behavior, I can write REG. So the color change, right? Because now we recognize this output, a specific signal is what? A register behavior. That means it will be involved with something related to clock. We haven't used it yet, but you know, I'm just telling you in advance. Make sense? So we keep it wire, or we don't need to write it. Sounds good? Okay. Now, how are we gonna build the full adder? The full adder, it was a bunch of XOR and 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 whatever, right? Do you guys agree?
Yeah.
Yes.
So if you remember, it was the CN XOR to AB XOR to what? To the B. That will be the C out, right? So in that case, I can say XOR 3. And in XOR 3, I will write what? FA, Scheiße, FA port out. That means I wrote the output of the process of XOR first. XORing here, FACN, XORing FA port A, XORing FA port B. That makes sense so far? So what does it mean here? It means that Muhammad XORed B with A and CN and the output written in what? In a FA port out. So far, so good.
Is that 3 supposed to be after the XOR?
3, it means that, you know, 3 input XOR.
Oh, I see.
So if I don't have 3 input XOR, I can use one single XOR. In that case, I will define intermediate stages, right? Like,
Right.
you know, I have A and B XORed, and the output of them, it has a name, it has to be XORed with the other port. Do you agree?
Yeah.
In that case, we have to define what? Here, intermediate what? Wires. So we're gonna define wire, and this wire will be what? FA XOR intermediate. Right? Then we're gonna do something similar, which is what? XOR, and we open and close. FA XOR end. That will be what? Output of XORing 2 of the inputs. What is the input I would like to have? FA port A, FA port B, and perfect. But this is not the final solution to bring me the sum, right? The output of the thing. I can call this to make it easy for me, sum out. In that case, when I change it, there will be an error here. So I have to go and change the name to be sum out. Have you noticed it's already highlighted to you? That means, you know, something wrong in the syntax.
Does it matter if we have a space after the commas?
No.
Okay.
No. Actually, I will do something in front of you, even more fun. Look. What do you think? Better, right? you can actually remind yourself as the following and say that, the output port of the XORing, right? First input go for the XORing, right? Here, second input for the XORing gate. Sounds easy? Now, this is not the final. We need the equivalency of what I have down, right? So I'm gonna make another XOR, right? Then I close it like that. And I start sort. So what is the input? What is the output of this XOR in this case? Is basically the FA port sum out, right? What is the two inputs? It will be the output of this guy, right? With the last thing that I haven't used, which is this guy, right? That makes sense? Now, there is a redundancy here, right? Do you guys agree? Because I'm porting out here twice using two different techniques, this one or this one, right? So it's better for me to comment out one of them so I will not have a race condition. Because, don't forget this tool is describing what circuit. That means it's also looking into the physics part of the circuit. Do you guys agree? What does it mean when I said, imagine something going into the output here, something is going into the output there, right? The tools will be like, what the heck? Is this guy taking the output from here or the, right? So you have to be sure that, you are defining correct. Otherwise, simulation will be wrong. And I will show you what does it mean wrong. Okay?
Professor?
Yes, sir.
I had a quick question. So is
Sure.
XOR a pre-existing method within Verilog? Or is that something you're just creating?
I didn't create it, but I can show you how to create it. But in general, have you noticed the color? Look at the color.
Yeah.
The color showing you that it's a part of the embedded library of the Verilog. See the color here, the color here, the color there, the color here. That means those are the embedded syntax inside the Vivado, inside the Verilog.
Oh, okay, that makes more sense.
Okay, now we finished, if you notice, the sum out of the full adder. Do you guys agree? We need the second part of the circuit, which is what? The ending. So, of course, we can have two ANDs that will be XORed later on, right? I think it's a 3 AND XORed, right? So in that case, we are in need of the wire of the FA and int1, wire FA and int2, wire FA and int3, because there are three There are three ANDs going into the circuit, right? If you remember from the design of the full adder, right? This is another level. So what we can do, we can write here intermediate wires for the XORing part. We can come here and say, intermediate wires for the ending part, right? Somebody will tell me, is it possible for me, instead of writing wire, to collect them in one side? Yes. So look, the other option for you is to write wire, and you take them with a comma. In that case, you just need to comment out those, because that will be redundant. So either that you can make it wire, or just one wire, and you start having the category that will be running for all of them as a wire. That makes sense?
Yes.
Okay. Now let's get the luxury of the wire, right? So we can come here and say that, you know, this is the circuit for generating the sum of the full adder. Here, we can write here, this is the circuit for propagating the carry out of the full adder, right? And here we can write what? And open and have you noticed something? The third one didn't actually get into a purple, right? Because this language is a case sensitive. It has to be lower, right? In this case, I'm gonna write what? And it will back. The line in front of you, this red, it show you that, you know, I didn't fill anything inside the and. That means something is completely what? Wrong. That makes sense? So in that case, we're gonna start taking into the consideration our output here. So this is the output of the first one, the output of the second one, the output of the third one. Sounds good? Now, what are the inputs of the first one? First and it's gonna be what? It's gonna be the FA CN with FA port A, right? Then if you notice, that thing is have been cleared, there is no more errors associated with it, right? Everybody agree?
Yep.
Now we're gonna move into the other one, which is gonna be what's A and B, right? So gonna be FA port A, FA port B. Then the third one is gonna be what? FA CN with FA port B. So far, we already got the three different combination and then from the three different propagation that we have from the input CN and A and B, right? Now, to get the output, we have to XOR, OR, right? Either that you're gonna make it OR 3, that means, you know, you have 3 input, or you're gonna make it 2 levels of ORs, and it's better to do 2 levels of OR for, like, you know, further what? Practicing. So here you can say that, you know, intermediate wires for the ORing part of the FA, right? So I have here how many wires? There is 2 ands going in one OR, and then, you know, this 2 together will get with the last one, they're gonna be the final output. So I just need 1 wire, right? So FA or intermediate. Then I can go here and what? This is the circuit for preparing the carry out from grouping and outputs in the FA, right? So I'm gonna say here or, then or, then. Sounds good? So the first or, it will be this, the output, and the second, it will be the official output, basically which is this guy, right? Sounds good. Now, what are the input of this? It can be this one, right? With this one. Make sense? What is the input for this? It's gonna be this one with the third, which is the NC. So officially, I have what? Officially, I have what? I have built the equivalency of 1-bit full adder using git levels implementation. Any questions so far?
Could you scroll down just a little bit?
Yes, sir.
I fell behind just at the end there. Thank you.
Just to clarify, you had XOR 3 earlier, and then you changed it to XOR. What was the reason for that?
No, I'm just showing you that there is other way, which is building just 2 input, 2 input, 2 input. Right?
Okay,
So
okay.
the 3 input is basically a bunch of 2 inputs, right?
So
If
the
you remember.
XOR 3 you meant was 3 outputs?
3 input, you mean?
Oh, okay, I got it.
So, do you remember what is the definition of the gates? If you remember, right? You have bunch of inputs and 1 output, right? So the number of inputs for AND gate is what? 2 or more. Number of the input for the XOR what? 2 or more. Number of the input for the XOR what? 2 or more. Number for the input for the XNOR is what? 2 or more, and so on, right?
Okay, that makes sense.
If
Thank
you,
you.
yeah, if you would like to build the tree of them, it's gonna be output and you propagate output and propagate and so on, right?
Right.
Anyway,
So we don't put a number if it's only 2 inputs, right? Only if it's 3 or higher.
yeah, because
Okay.
those are new. Those are new. Have you noticed even when I made it, it didn't give a color of the like this, right? Because those are the new generation Verilog. It's not the old generation Verilog. Those old generation Verilog, that's why they give you a color, right? Can you hear me?
Yes.
Sounds good so far?
Yep.
Professor, so is the XOR 3 a predefined Verilog function, or is it something like the user has to define it themselves?
It can consider predefined, but it's not really in the old version Verilog. It's a newer version Verilog.
I see,
That's
thank
why that's why you need to go and change here. Look, do you see this long line? They used to say here, like, advanced Verilog, what version of Verilog? But this is an older version of Verilog, so it's 2001. Okay.
Yep, got it.
You can see even, look here in VHDL, I will show you. There is VHDL and VHDL 2008. Because VHDL 2008, for instance, is using object-oriented programming with Hadoop description languages. So it's a little bit modification, okay? Anyway, there is a question for you guys. How I'm gonna figure out that, Dr. Ali built the right circuit? Maybe I made a mistake, right?
We had to verify it or something.
Exactly. So we have to run what? Simulation before the emulation.
Yeah.
So simulation, it's the second part of the game, which I'm gonna share with you now. But before simulation, if you guys remember correctly, we said every single board, it has its own XDC file. Do you remember how I said that last week?
Sort of.
And the XDC file is called constraint file. It's called what? Constraint file. So to do so, we need to go into Google, because I don't like to remember anything. So I just go Google and I show you what I'm gonna do. So I stop sharing now, Vivado, and I'm gonna start sharing with you Captain Google. All right. And Google, I will write to him what? I want Nexus. I think the one I have is Nexus 4. Let me see. Yeah, it is Nexus 4. So I will look for Nexus 4. Nexus 4 DDR XDC file. GitHub has it. So I'm gonna go there and I will take a copy. Look, I'm just taking a copy. Sounds good. Now we're gonna stop sharing again and we go back to what? Vivado. Here is Vivado. Everybody can see Vivado?
Yeah.
I'm gonna say add, and there I will add or create constraint file. Sounds good? There I say next, create, and then I will call it what? Let's be more fashionized, so I'll just call it what? FA. To be the name with the module, right? Now, if you look here under constraints, you will find the file that I just generated. Can you guys see it? Everybody can see it, right? Now, I will double click. It's empty, right? I will say Control V, then you know a copy of whatever I saved, and go there. Sounds good? So the commented command in the XDC is under something is called TCL, tickle script. That's why we use what? This sign. So if I like to uncommented something, I will just go ahead and remove it like that. If I would like to comment it again, I do it like this. So far, so good?
Yeah.
Any question regarding what I have done so far? If there is no question, I will move forward. There is no question? Okay. Now, let me tell you what is the story behind all of these lines, right? So what is the story? The board we have, it has something is called external, it's called external what? External clock source, while it has internal clock source. So it has a crystal inside the chip, and there is one outside the chip. So the one inside the chip, if you would like to access, you have to comment it line 7 and 8. Then you will be able to use the clock. Sounds good? And this clock, it is 100 megahertz. It depends on the name inside the file. I'm gonna change the port here. But we are not using it so far, but I'm just showing you what I have. We are not using it now, but we're gonna use it. So far, so good?
Yep.
So if you would like to use the clock internally, which is 100 megahertz, you have to what? Uncommented these 2 lines. We don't need them now, so we're gonna what? Scheiße. We're gonna do what? We're gonna comment them out. Then, for those have the board with them, there is 16 switches we have on board. Have you guys had a chance to look into the video or pictures for that? Did any of you get the vote so far?
Not yet. Still waiting
Okay.
on it.
Okay, so we have here 16 switches. If you look in my camera, here are the switches. Can you see them?
Yeah.
Yeah.
Those are the 16 switches we have. They are on, off, on, off. In the top of each one, it has the name of the port here. J15, L16, which is the metal, bare metal connected to the PCB board. If for instance, I would like to use one of them, I will just comment it out. Uncommented, sorry. If I don't want to use it, comment it. So far, so good?
Yep.
Then if you would like to deal with LAD in the top of the switches, there are 16 LED sorted in front of you. If you look in my camera carefully, you will find them in the top of the switches. Can you guys see it?
Yeah.
Those from the line 33 to line 48 belong to that. So far, so good. How are we gonna communicate with them? I will show you. Okay.
Professor,
Yes, sir.
would it be an issue to keep everything uncommented?
It's better to be commented, and then when I need something, I uncomment it. Because if you uncommented everything, the compiler when is running for mapping, it will consider it an error.
So if you have it uncommented and you run the program, it'll consider it an error?
Yes, it will tell you where are these ports.
Okay, that makes sense.
Okay, you have to match the ports between the design and the constraint. Okay, anyway, now there are set of 50 to 55, which is the 6 lines. You know what is those, guys? Those are 2 LEDs are RGP. Do you guys know what does RGP mean, right? They're colored, right? RGP, red, green, blue. And those 2 are exactly laying here. They are there. Can you guys see them?
Yeah.
Yes.
In the top. Okay. Which is called LED 16 and 17. So each one, LED 16 and 17 has what? BGR, BGR. See, it's LED 16, 16, 16, 17, 17, 17. So far, so good?
Yep.
We're going to use all of these, so no worries. Now, if you look into my camera, how many digits we have? 8 digit, right? 8 7-segment display digits. Those 8 7-segment display digits, they are located into the Vivado from line 58 to the line 68. And the control of each one to turn it on and off from line 70 to line 77. There's a protocol for this. We're gonna learn also while we are taking 3300. Sounds good? Now we have buttons, like you push it, you release it, you push it, you release it. Where are those in the board? Can you guys look into my camera? Can you see those?
Yeah.
Those are the 5 in the top of each other. But there are 6. Number 6 is basically by itself are those 2 guys, the reset and programming. And there is a story behind it. I will tell you later about. Okay. Then we have something specifically made by Digilent. It's not belonged that much to Xilinx, but it's a Digilent invention. They call it PMOD, which is a high-end port that can be plugged into some of the sensors they already sell on their website. I think you guys, while you're buying, I'm sure that you saw some of them, right? It's called PMODs. How many PMODs we have? Look carefully on my screen for Vivado. We have A with its own ports. We have B with its own ports. We have C, and we have D, and we have XADC, and basically where those located in my board. Do you see this black connectors?
Yeah.
You see? 1, 2, 3, 4, 5. Those are the 5s we have. One of them is XADC. You know what is XADC? It has analog to digital converter. It has what? Analog to digital converter. We're going to work on it. And it's really fun. Okay. Now, there is here in 154, the VGA connector. We have what? The VGA what? Connectors. And that's basically the ports you can see on my screen here. Can you see it?
Yep.
And I will show you how can you program it. Okay. Then for advanced courses, if you guys like to, for me to teach you all of the tricks, I can teach you all the tricks. I love actually teaching tricks. Anyway, SD connector. Guess what? Where is the SD here? Can you guys see it?
Yep.
How are you going to communicate with it, and the layer of communication and formatting inside the SD card and communicating into a processor on the chip. That will be also good. Then we have the accelerometers. Accelerometers is basically a sensors laying on the board. If you when you will get your board, okay, when you will get your board from Digiland, they already have like a demo on it. You will find when you start moving like this, you will find out the gravity and the coordination on the screen. If you connect the VGA, it will be changeable, and it's really fun. If we have time, I will show it to you. If not, 4305, 4304, you will be able to study this. There is a temperature sensor, and is using a protocol. Is called SCL, and this protocol is basically called SPI protocol. Have you guys heard about SPI protocol?
No.
No.
It's a protocol used even for microcontroller. It's called SPI. You guys took microcontroller, right?
Yeah.
And you didn't hear about it, right?
Oh, we're taking it right now. Or I am.
You're taking it now, right?
Yeah.
Okay. And here is the temperature sensor. Can you see my finger? It's pointing there. Okay. Now there is a microphone. So there is a directed microphone. We can connect into it here. Can you see it?
Yes.
And that's also using a kind of SPI. And there is audio amplifier also inside the jack. And there is what USB interface. If we're gonna learn about something, it's called UART, and this is coming from the JTAG cable here. In the back of it, there is a chip here, and this chip is called JTAG. We're gonna teach UART in this course as well. There is HDI, so the USB also, it actually can be split to be a USB, or it can be using for the high definition interfaces, and that also using a kind of advanced SPI, and you can actually use a mouse to move or build gaming on the board. Then there is Ethernet. Here is the Ethernet. Guys, can you see it?
Yeah.
So the Ethernet here, those are that belong to it, and there is two different protocols inside the Ethernet. We can talk about them. One is called TCP, and that's why it's called a DHCP. And I don't think we'll have time for it, but I will try to give you like introductory for it by the end of the course. Okay. Then there is SPI flash. SPI flash, there is a flash drive in the top of this. You can connect to it and store data if you are out of memory on the chip. And I don't think we will need it immediately for this course. So far, so good?
Yep.
Now, there is a missing hole here, right? Dr. Ali talked to us about full adder, and then he moved to the constraints, right? What are the relations? So we're gonna talk about it, but beforehand, we need to start testing whether the full adder Dr. Ali made is correct or not, right? So in that case, we need to write a new file, which is called what? Test what? Bench. So out of this category, it will be what? Add or create or simulation sources. Sounds good? So here next, and here create, and then we're gonna call it what? FA test bench. So far so good? And we say okay. In the test bench, start asking me about input and output ports. But in reality, rule number one in any test bench, there is no input and output ports, because you are actually wrapping your interface around your block, so you can start pushing input and output there. That makes sense? So in this case, I will just say okay. Then you don't have any change. I say yes. Okay, so far so good?
Yeah.
Okay, now where is exactly this guy is located? Simulation sources, you open, it's called FATB. There I can select it as what? As a top hierarchy. C is the top for the simulation, while FA is the top for the design source. Have you seen what I have done?
Mhm.
I clicked on it, and then I set as a top. So it's already at top. That's why, it's not allowing me to do that one more time. Then I will open the file. As everybody can see, the file is what? Empty. It's following what we learned from the last week. We module, the name of the module, the list is empty, and we end module, right? And the file is also .what?
.p.
.v. So what we need to do now, we're gonna learn the second trip of the Verilog, which is called what? Instantiation. What does it mean, instantiation? We call a module inside another environment module. Like what we did with 2300, you already have the IC-TTL transistor, right? You have in front of you the manual, the data sheet, right? Then you start say, oh, I have to connect here resistor, I have to connect here resistor, here is the current source, here is the voltage source. Then you can see stuff coming out of the IC, right? Same thing. Where is the IC we built? FA. So we need to call it inside what? FATB. So far, so good? Any question?
No.
Okay, now I'm gonna do a trick in front of you. Okay, second. Okay, now the module I'm gonna call, because I like to test, is this guy, right? But I don't need to take all of the internal wire, whatever. So to instantiate, you take a copy of this couple of lines in front of you. And you go inside the FATB and you what? Copy it. This is the first step. Okay? Sounds good to everybody?
Yeah.
There is an error will happen. I love errors. Okay? So in that case, we need to instantiate. How to instantiate? We go here and say, remove this module because it's no longer module. And it's basically, for me, it's called FA. So I'm using the full adder, but I might call it multiple times. So I have to give name to this specific component I'm calling. In the test bench, I will just say what? Comp1. So what I did in front of you, I instantiated. That means, I have full adder, but I call it inside the full add the test bench. I call it what? Comp1. So far so good? Okay. Now there is two ways for instantiation, and we're gonna see it and visit it in the slides after we finish this example. So one of it is basically, it doesn't matter how you're gonna sort the input and outputs. It doesn't need to be exactly the same way I ordered in the full adder. I can put it in any out of order, which is basically you remove the input output and you put dot. You remove the input output and you put dot. You remove the input output and you put dot. You remove the input output and you put dot. And you remove the input output and you put what? Dot. Are we done?
What is that for again?
Those showing me that full adder is an IC and it has ports, and those ports are input and output. Sounds good. I'm calling the IC, right? Consider the FA underscore TB is your breadboard. And I bring in the FA and I'm putting it in the breadboard. Right? You understand what I'm saying, right?
Yeah.
Okay. Now, those has to be connected to wires I'm gonna connect in the breadboard. So you have to make it what? Parentheses. See? So now I am ready to connect the stuff inside. Like, my data sheet said, there is a input, it's called FACN. I have to connect wire to it. And that wire will be holding something. I don't know how I'm going to make it hold. Okay. So that means I have to define the environment around the IC, right? So there I will call it what? Define the environment around the module. In our case, it's FA. So far, so good. Do you agree?
Yeah.
Okay. Now, if you remember, when I was in the FA, I told you all of these guys are wire, but if the output changed, it will be registered. Do you guys remember that?
Yes.
Yes.
And we said when the output will have a kind of like a storing behavior, it has to be registered. Okay. Now, if you go in there, in the test bench, you have to be sure every single input. You have to be sure every single input is what? A register. And every single output wire. Because end of the day, the input will be, moving from state to the others, right? Because I'm trying to push input inside the block and see what is the output, right? So there I'm gonna say register, and it's gonna be FACN test bench. And it's a single wire, or it's a single bit or multiple bits? Should be single bit, right? Exactly as the CN, right?
Right.
Then register FA port A test bench. Is it single bit or multiple bits? Still single bit. Register FA port B TB. That's also another single bit. Are we done with inputs? We are done with
Yes.
inputs. Then we're gonna define what? Under this, we can say defining the output wires for the FA module. In that case, it's gonna be what? Wire FA port sum out TB, wire FA port C out TB. So far, so good. Now, I need to take those names and I connect them, because those are the wires I have in the lab, and I'm in the breadboard now, right? So I connect this to here. I connect this to here. I connect this to here. Then I connect this to here. Then I connect this to here. Have you noticed? There is a blue lines coming everywhere. You know why? Because I instantiate before I define. So what is the best practice is to define, then you instantiate. Did you see? I made a mistake by what? Intentionally. To show you that fixing it, you have to, first of all, in the test bench, you don't have any input output ports. You have to define what wires you will need or registers, and then you start inserting those inside the ports of the input and output and inside the module. So far, so good. Now, you know, my chip I designed is called FA, which is a 1-bit full adder, ready to accept anything going inside input, then we can see it as an output. So far, so good.
Yep.
Now we're gonna use something, we're gonna learn it in details later. It's called initial block. Initial block, which is a static block used to insert a certain event of the inputs and monitoring the output. What's called again? It's called what?
Initial block.
Block. Initial, begin, end. And we can give it a name because we can actually have multiple initial block inside one test bench. And we can call this what? Test case 1. You don't like it or what? Oh, sorry. It doesn't go in initially, it go into the beginning. Sorry. Okay. So what Professor Ali did now, I built the environment that I start injecting inputs inside the full adder. Sounds good?
Sounds good.
Then there is you know, the input when I will put it, how many inputs I have? I have 3 ports, right? I have the CN and whatever, right? So first of all, now I will take this as my input, right? And I will say it's equal like this. You see, less than equal. This line equal, it's something we're gonna learn later, and it's called block and non-block. But you can make it equal if you want, because it is bench, right? So you are in luxury to make it like this, or you can make it like that. Okay? You can put decimal in it, so you can say 0. What does it mean? Connect ground to this wire or to this input at that moment. Okay? Sounds good? I wrote it decimally. All of this will be in those slides, but I'm just like to make a practice in front of you, okay? Other way to present it. That guy was what? Single bit. Do you guys agree?
Yeah.
In that case, we can write it in binary, right? So it is 1 bit, B is binary, and it's holding 0. Did you see what I'm doing?
Yep.
1 bit, it is binary, and it has 0. Super. Then the second input equal, I'm gonna make it decimal, right? So 1, D 0. Then comma 1, you know, instead of like this, just do it like that. Okay. If I don't add anything else than that, if I run the simulation and look at the waveform that will be generated out of the test bench, those guys will be zeros forever. But this is not the right thing, right? Because I would like to see if I change cases, what will happen. Do you guys agree?
Yes.
So the question for everybody here, right? Since I have 3 inputs, how many cases these 3 inputs will generate?
8.
8. So the best way to represent it in time is what? To force a set of the state, you will add delay, then you will force another set of states and so on, right? How? Since, you know, initial is just run 1 time, right? So then, you know, I can just start adding time. So what does this mean? It means that I added 10 nanoseconds for those guys to be zeros. So those guys will be zeros. 10 nanosecond, I will do something else. So in that case, I can do what? I can take copy of this and put it here. What did I do? Scheiße.
Professor,
Yes.
does it have to be D0 or B0, the second line for port A?
It doesn't matter. It can be anything. You know, it's up to you. You know what? Here, D.
Okay. Oh, I
Right.
thought it stands for binary. That's fine. Okay.
Oh, no. There is no need for order, you know. Anyway,
Okay.
copy. Also, you don't care about order. You can bring this guy here. You can bring this guy here. You know, it doesn't matter, right? You understand what I'm saying, right? So I can make this, for instance, B, and I can make this A, right? But, you know, normally it's better for you to do it like this because, you know, we're going to do manual movement, right? So here is what it was 1 0 0. So going to be here 0 1.
So are
When
those
I give
the
you the-
ports on? Sorry, Professor. Are
No,
those
go ahead.
the ports on the board, or are you
What is it?
defining like the? Are you like defining the ports on the board, or?
It's not board. I'm not using the board yet.
I know, but you are defining the inputs from it. I don't know, like what.
No.
things you are
Basically,
defining.
you know, I will tell you. What I did is the following, right? FA, it's a module I wrote, right? I would like to test whether this FA is running correct or not before I would go to the board.
Right.
So I already instantiated this FA. I instantiated this FA and I put it inside the test bench. And the process of instantiation is to define wires and signals of input and output of the test bench. Then instantiating as I showed here. And after that, I start generating different input patterns. Then I will look in the waveform to see whether the output is expected or not. And if the output is correct, then I will move to the third step in the row, which is basically what? Connecting to the board.
Okay.
Sounds good?
That makes sense.
Yes. So anyway, I will add a couple of cases, but you guys can later on add more stuff because I will give you a copy of this, right? So for instance, we have something in circuit is called corner cases. Have you guys heard about it?
Yes.
In corner cases, we are looking for something might generate or propagate an error, right? So one of the cases I would like to check is what? If all of them ones, what will happen? Carry out will be coming out, right? You guys agree? Then I can and put like a good decent amount, and then I say what? Finish. What finish? It's an order to the waveform to stop processing. And the waveform, it's a window will be open when we start running this code to check whether it's running correct or not. Okay? So far, before I jump and show you the waveform, is what I already mentioned clear so far?
Yeah.
Okay, for those people who believe it's not clear, you know, I'm here to make it clear. So stop me now and tell me what's the problem so I can go back. Tell me.
What's the difference between using the pound symbol here as you're having a wait of 10 nanoseconds or something,
Yes,
but
sir.
on the other sheet you use the pound symbol as a comment? Like,
sure, because you know they are different environments, right?
okay.
So the dot V, this sign, it has a meaning in the test bench like that. But you know, in V, you are not accepted to do that because you know. Do you remember when I said there is a set of syntax will be used for test bench, will not be used in RTL, and there is a set of syntax in RTL will not be used in the test bench.
Mm-hmm.
This is what I meant.
Okay.
Then XDC is not even very long. XDC is something is called TCL. It's tickle script. So
Oh,
that's
okay,
why,
I
you
see.
know, you got my point?
Yeah, I see it now. Thank you.
Sure. Okay. And any other questions?
Oh, yes, Professor, could you describe what the reg keyword is again?
Which one?
If you scroll, yeah, like
The
when
reg?
you do inputs, yes.
Okay. So the reg is a register. So the data type, there is different type of data. There is a wire, there is reg, and there is even, you know, in system Verilog, there's something called logic. But for us, it's just reg or wire. So reg is the wire that will be going with clock. That means gonna go in a flip-flop, for instance. So gonna, end of the day, storing something, right? But wire is just a wire. It's a connection between point to point. There is no delay might happen inside. Okay?
So like reg is kind of like something that stores like a variable or something like
Yeah,
that?
you know, it's gonna be involved in a process to store.
I see.
Again, so for instance, here in this context, right, why I make input registers? Because end of the day, I assign values here, right? I keep assign value with time, right? It's a kind of element storing, right? Do you agree? Because it changes with the time. But in the wire, you cannot do that, right? The wire just pass. It doesn't have, you cannot say in the wire after 10 minutes be something else, right?
Yeah,
It's just a wire.
I think I get it now. Thank you so much.
You're welcome, sir. So what, anybody else, you know, listen, the foundation is the most important part. Once the foundation is set, we can work like, you know, fantastic. So anybody else has any hesitation, concern, raise your hand, or, you know, go ahead and talk and I will go ahead and help. Anything is confusing? Somebody was stuck in, I'm checking the chat. So the Sublime is great. Sublime is fantastic. Muhammad, you said case sensitive. About what? Muhammad? Okay. Okay. Sounds good.
I think,
Now-
yeah, I think
Yes.
that was when you changed the AND gate to capital
Oh, yeah,
letters.
yes.
That was a while ago, yeah.
I just would like, you know, I would like to see what's going on. Okay. Anyway, now we are ready to see something new will be popped out. It's called waveform. Waveform, which is representing the values of signals, input and output with time. Okay. How are we gonna pop it out? So since I already made this as a top file for this bench, and this guy as a top file for design source, I'm allowed to run here in the site something's called run simulation. What's called run simulation. If you click on it, it will run something is called behavior simulation, which is a phase of simulation, doesn't have any synthesis process in it. Just my code and I'm testing it. That's called behavior simulation. There is later on some other captions here, like, you know, post synthesis, timing synthesis, and so on. Those can come when we start running the process to generate bit stream on the chip. Okay, let's test it. So we're gonna say run behavior. Now is executing an analysis, what compilation steps. It's taking some time. Okay. Any questions so far? It opened. Can you guys see it?
Yeah.
It's cool, right? Look here. Look at this. Here is the tree, right? Comb 1, it was the full adder, but we call it comb 1. Do you guys remember that?
Yeah.
So this process is called what? Instantiation. What's called instantiation, right? So I instantiated, and there are the values of all the ports I have under comp 1. If I go up here, it will give me all of the signals of the TP. You guys agree? So that can help me to do what? For debug. If I would like to debug what's going on with my code. I can go, I don't care that much about this pitch. I care that much about what is internally, so I can see what's going on. All right? What internally, if you guys remember correctly, we have the intermediates of the and or and so on, so you can propagate and see whether that your code is correct or you connected something wrong. Sounds good? Now, the waveform here, and we need to see what's going on. Huh? So click here. Sounds good? If you move a little bit here and start going like that, you will find out if CN0 and the port B0 and the port B0, what is the output will be?
0.
Exactly, 0. And what is the carry out will be? 0, 0. So far we are great in this state, right? After 10 nanoseconds, see 10 nanoseconds there. Can you see it? Can you see the 10 nanoseconds I'm highlighting in it?
Yes.
This one, right? What happened? I made the CNTB up high while the other is low. So what is the output will be? Huh?
1.
1. Here is 1. Then after 10 nanoseconds, I made one of them high, which is A, and the rest is 0. The output is still what? 1. You guys agree? Then after 10 nanoseconds, I decided to make everything high, which is end up making what? Sum out 1 and the carry out 1. And I haven't changed it. I just run it forever. So that's why everything went high all the time. So that means my design is correct so far. You guys agree?
Yeah.
Yes, makes sense.
Tell me why you think so. Tell me. Mario, is it clear or do you want me to clear it?
No, that's clear. We get in the expected results.
Anybody has any problems so far?
I actually have a question, Professor, about the test
Please go ahead.
bench. If you
Sure.
could go back.
Yes, here.
Yeah.
Yes,
when
sir.
we go through the cases in test 1,
Here,
are we
yes.
yeah. Since there would ideally be 8 different cases, we would have to go through them manually. Like, is there a way?
That's a very good question. No, I mean, there is other syntax I will teach you that they're
Okay.
gonna make it faster for you. You can make it with for loop, you can make it with while and stuff like that.
Okay, sounds good.
That's a
'Cause-
good question for sure.
Yeah, because with the 4-bit adder, it'd make it pretty.
It's too much. Imagine what about 4-bit?
Yeah.
Definitely, I agree with you. Plus, also, we're gonna learn about something is called parameterizing, because 1 bit, 2 bits, how we're gonna do it, and so on, right?
Okay, sounds good.
Okay.
Thank you.
You're welcome, sir. Any questions so far, guys?
I was following along with you and I built it myself, but I'm getting errors when I'm simulating. So you said that we're gonna have what you built available to us?
Definitely.
Okay.
Anything I do, copy for you.
All right, awesome. Thank you.
But I will use when rare for compressing it, right? You guys know what is when rare, right?
Yeah.
Okay. Also, don't forget, I'm using 2018.1 Vivado.
Do you think that'll cause problems if we have a different
It
version?
might sometime,
Okay.
but you know, I don't think it will give you an immediate problem because I'm not using any IP. There's something later on I will show you, it's called IP, but you know, I think for this specific moment, I don't think so. Should be fine.
Are you gonna be using this 2018.1 for like the whole semester?
I believe so because you know my computer is really it's
Okay,
not
yeah, so
powerful.
I'll probably just get that same one then. Because I've tried to download 2019 and I'm getting errors, like it doesn't let me download it.
Ah, by the way, 2019, they discover some error and that's why they make 2020.
Oh,
I am telling you, it's
I know, I believe you. So you
This-
say you had 2018.1, right?
yeah,
Okay, thank you.
2018.1. This is one, you know, I tested million times. So that's why, you know, I brought it back. Okay. But of course, you know, the new one, 2021.2.1, it's a machine learning version. That means they're already embedded inside the Verilog IPs for machine learning. But it needs a heavy computing platform. My computer is like Microsoft Surface. I don't think, you know, Surface is meant for heavy computation. Okay, Luke?
Yep.
Okay. Now, there is a question. Is this, from your point of view, possible for me to create another instantiation out of this?
Yes.
Exactly. Like, you know, you went to the shop, in the Fry's or, you know, Micro Center, and you told them, I would like to buy 2 full adapters, right? And you would like to connect this 2 full adapters together and build something, right? Do you agree? So there is 2 ways for you to do it. If you're gonna connect them in RTL, it's completely different than if you connect them in test bench. Do you agree?
Yeah.
We're gonna look into that. But beforehand, Angie basically asked me a question, which is very good. Are we connecting anything to the board? So it's a time to connect something to the board. And after that, we can return it back to any other possibilities, right? So succeed, you know, we succeed, right? We tested. Now we can close the environment of the simulation. We don't need it now. Thank you, simulation, right? It takes some time, right? Yeah, okay, close, thank you. Now, what is the connectivity between the FA.V, which is the design source, with the XADC? I will tell you. Now, for FA.V, we have 3 inputs. So from your point of view, those 3 inputs on the board, they can be represented by what? Switches or LEDs or what?
The inputs would have to be switches, no?
Or buttons?
Yeah.
Yeah.
And of course, the output can be what?
LED.
Do you guys agree?
Yeah.
Yeah.
In that case, we're gonna take the name of the 3 inputs, FACN, I will take it, and I go into the XDC. And I will search where is the switches, right? I found here switches. So I can take the first 3 switches, 1. Maybe I can keep switches in the middle, doing nothing, right? So the 3rd can be another one, and the 4th can be another one, right? But the names of the switches is called switch, but the name here is not switch. So I have to match names, right? So in that case, FACN can be the first switch. So you have to identically match the FACN there with the XADC because you connect, right? Like you are wirelessly connecting. Then the other one is port A is going to be there. And the other one is called what? B, right? That will be connected into the our force. So now we are guaranteed that, you know, the XDC is connecting the bare metal of the board with the soft module FA we already built when we run synthesis. But still, we have outputs, right? How many outputs we have? We have two outputs. We have the port sum out and the carry out. In this particular case, we need a device representing the output. What thing on this board can represent the output? LEDs,
LEDs, 7-segment.
or 7-segment display, or VGA, or something, right? So in that case, I'm gonna go in LED, as it's really quite easy. So maybe to make it really easy for us to distinguish the changes, we can make the first one and the last one without color. The one will be sum out and carry out, right? So I can go here literally and I take this as a copy. No, Scheiße. I go here and I just go here and say carry out. Like that. Right? Then I go here and I take the port carry out and I put it there. Did we forget anything in the list of input output that is not connected here?
No.
We didn't. In this case, we're gonna start a long process, which is called synthesis, place and route, and also generating bit stream. But to be qualified to do this, we have to connect our board with the proper JTAG cable that will allow us to deploy the file. It's called .bit, which is bit stream, into the board. So the board will perform exactly as a full adder. Okay. So let me see if I have the right cable. Where are the cables? Cables. Yay. I think I destroyed something. Let me just see if I have cables. Sometimes, you know, the board will be missing something. It's called DigiLink cable, but we have to do it. So it depends on the final answer. Let's see. So I think I have a couple of them, so I can use one. Okay, here we go. So here is my USB. Here in my hand, can you guys see it? And then, you know, I connect it to what? My board. Everything is connected. You can turn it on the button and I think it's connected. I think so. And I can go here and I say USB. Yeah, I hear something. So basically, it's yeah, it's working. It is now on. Can you guys see the line? Everybody can see my line? Why this is the wait? 1 second. Let me see what is the connectivity. Is correct. Should be SD. This should be. Okay, I just connected. Okay. Here in front of you guys, everything is turning on, right? Now everybody look into the Vivado. So look what I'm gonna run. So if you look very carefully after I set up the right jumpers, look what's running on the board. Can you guys see what I'm doing now on the board? There's some sun running like a snake, right? You know what is this? And the coloring LED is turning on and so on. You know why? Because the demo that in SPI Flash that dedicated by Digilent is there. We can override it and put whatever we want. Is it clear?
Yeah.
Okay. Now we're gonna go into the process, right? So here it says run synthesis. Can you guys see that? You're gonna run a couple of some steps, but you know later on I will tell you what is what. Okay. We say here run synthesis. We say that save XDC. Yes, we save XDC. And how many thread in my computer? I have 8. So I can use it because this tool is using what? Numerical modeling. So as many thread involved, that will make it finish faster. Okay? Sounds good? It takes time. Can you guys see there is like in my screen, there is like a green dynamic circle going around? Can you see it? Yeah, this means that, you know, is running. And to be sure that, you know, there is a message here generated, look. And in the TC console is telling you there's some stuff is happening in the middle.
Can you scroll down to the LEDs?
The LEDs?
Yeah, because I think you no on the XCC.
Yeah.
Okay, because you put C6 by accident.
That's good, that's good. It will make error.
Oh, okay, cool.
Let's make it error, right? You know, good to have an error, right?
Professor, I have a quick question.
Two questions.
So like when we synthesize, are there any consequences of having errors in our code? Because we're dealing with like bare metal. So can we like fry anything?
No. That's why, you know, strategy normally when you write a code, you run a test bench. Strategy. You know why? Because if you keep trying and run synthesis and you keep trying and run synthesis, what will happen? You will hurt, you will be tired. You know what I mean? And it will take too much time. So that's why test bench can early telling you what's the problem, then you can fix it before run synthesis. As you can see, it's taking forever, right? But you know, consequence on the board itself, no, shouldn't be.
Okay.
You already have a protection. But I figure out a way to override the protection. But I'm not gonna tell you about it. It's a trick. You have to pay for it. 15 cents. It's taken forever, which is cool. I love that.
For the Sublime, how do we incorporate it with Vivado?
Did you see the way that I'm writing here code?
Yes.
I will write this next code in front of you outside Vivado.
Okay.
Then
Okay,
you
so
can understand what I mean.
Okay, so you just write it outside and then you copy it in.
No, it's not copy. It's just add, and I will put the location. That's it.
Huh. Okay.
Good trick, right? So census is passed, which is actually correct, but it's not correct as one of you figure out that I wrote Z6 or whatever, right? So who will gonna fail? Implementation. So if I run now implementation, it will fail. But while we are looking to the result, it will tell you that I use one lookup table to implement our full adder, which is the combinational circuit. Okay. Do you remember when I was showing you the resources on the chip? I said lookup table, DSPs, whatever. So this is what we use out of the whole entire board. So that's whole entire full adder code we wrote is this one lookup table. Sounds good? While we are waiting for the implementation to fail, I'm gonna show you some stuff fancy, okay? Fancy stuff. Schematic. So I click on a schematic. Can you see it?
No.
It's taking time because my computer is the most accurate, fastest, wonderful laptop in the nation.
What did you click on?
Schematic. Under the synthesis, open synthesis design, schematic.
Okay.
It's taken 60%. So, there is an hope, one day in 17 million years from now. What is this? This is the chip. Did you see that thing that is open in the beginning? That was a chip. And look what we implemented. This is our implementation. See, here's the inputs. And the inputs donated was what this sign of buffers. And here are the output. And those are the lookup tables, which is they call it 3-1 lookup table. See, 3 input lookup table, output. And then, the buffer output is connected to the output ports. So this is the equivalency on the chip of the code that I wrote. Those together, they consider them what? One LUT6, even though that is LUT3. Okay? Sounds good? Wait for this to fail because I'm waiting to fail. Yeah, see, failure will happen. Why? Because it started giving us here warning, which is a lovely warning. When the warning has a different color. Some warnings is useless. Some warning, it's like it's a bad thing is happening. You know what I mean?
Yeah.
So you better to take care of them before it will turn to be big scheiße. Elapsed time, okay, message time, that's good. Hey, dude, come on, fail. No way. I passed this, so that means it's gonna fail in the generate bits tree because they're metal. Okay. Maybe it has to give us like a critical warning because this is weird. Let's stop this. Let's see the warning. No port match. See Z6. Huh? Everybody can see it?
Yeah.
No port. That means it's better for us to stop this because it will fail in generate bits tree. So here we can say what cancel. There we can just go into the XTC and we can remove what? Yes. Let's save. When I save while we are running, it say what? Reload, because something is in action happening and we have to change it, right? Do you agree?
Yes.
So there we can say stop. It's initializing. It will rerun again. After we finish this, I will move to the slides so we can learn more about the language so we can start using it, okay?
Okay.
But at least you guys understand what I'm doing, right?
Yeah.
Is it sounds fun to you guys? Yes. Okay. I said stop in the background, that's fine. Then directory, okay, go into it. And then I go here and then I say script. See time run. Then there Taking more time, right? Mhm. So takes some time, so maybe we can start talking about the slides and waiting for it. What do you guys think?
Sounds good.
Yes, so 1 second to share the slides with you. Okay, anyway, I think it's better to stop the sharing and leave it running until it's stopped. Then, I will show to you what's happening, okay? Because, just, you're not gonna miss anything. You're gonna be run synthesis, after that run implementation, then programming and debug you run, generate bitstream. See, there is like gray because it's not ready, right? So when you run it, and after that, when it comes to this point, I will return it back to the tool, okay? Now, let me share my screen. I'll say run, right? So you run implementation, we run, but it's okay. So stop sharing. Go to Mohammed. Yes. You guys can see my new screen, right?
Yes.
If you remember, we stopped here, right? We said that, the module, and here the module name, and we already have done this practice, right? And we made the data type declaration and the circuit functionality timing specification we haven't talked about yet, right? So for instance, if you also remember when we made the full adder example, right? We came and we said, oh, are the input is gonna be a single bit or multiple bits, which we call a bus. Do you guys remember that? That, for instance, is basically what a bus consists of 8 bits, 7 to 0, right? For instance, clock and CLR, which is clear, those are single bit inputs, right? For instance, out, it's basically 16-bit as an output. And also we mentioned, if you guys remember, the type of ports of coming for the module are input, which is input port, or the output port, or in out, which is bidirectional. Like, in the memory, for instance, you can actually use the same bus to store data in a memory or looking data out of the memory, right? How can you have a port declaration? You declare the type of the port and the name of the port. If you guys remember when we say that, input, and, we call it port underscore A or whatever. Sounds good? So we already practiced this in the example we had of the full add, correct?
Yep.
Then, when we talked about data types, like, there is a different type of data, and the data here is called net data types, which is representing the physical interconnections between different structures or modules, like module here and module there, right? And some of them are nets and some of them hosting variables. So they call this what? Variable or temporary storage. And the different type of the net data is basically wire, as I told you, and is representing what? Noodle connections, or logic, and I told you that specifically in a higher version, they have it is called logic 0 and 1. But the most important thing, if you're gonna make a variable, which is gonna be ring. And we already defined how can we define it, right? Anybody remember what does try mean? Do you remember in the 2300, try, it means tri-state. Do you guys remember the tri-state? Hello?
I'm not sure.
Yes.
You didn't take it?
I absolutely did. Just foggy.
That's fine. Anyway, who was teaching you 2300?
Adrian Gonzalez.
Okay. Anyway, that's called tri-state buffer. So if you put here 1, that will be a wire. If you put here 0, that will be open circuit, something like that. Okay.
Okay.
Anyway, we're not gonna use it. I'm just telling you an example, right? And I already defined this bus in front of you before, so you know it, right? Here, for instance, the registers, right? The register can be a set of wires, or it can be whatever you would like to have. Oh, by the way, the thing now went in a generate bit stream, so maybe we can stop here and back to see how it works, and then we can continue. Okay. Everybody can see my Vivado?
Yes.
So now let's say what? Implementation design or generate stream, or it should be generate stream. Okay. So stop here, and it should be faster. Okay. Look here, some information, right? Because we are using direct IO, input output ports, look at the amount of power we are consuming. See, 2.18816. While I'm working in this course, I will be teaching you how to work in the low power mode. This is the lowest you can get, by the way, with this specific example, because you are using 5 output devices, switches and LEDs. If you decrease number of LEDs and having muxing and stuff like that, the power will significantly go down. Okay, but one lookup cable is used. Somebody wrote something. Let's see. Is that total power in watts? It should be, yes. But sometime the inside the model they change it to be milliwatts or microwatts, or whatever you want. Okay. So it shouldn't be taking that much time, because it's generating the stream. Okay. See, we are not using any clock, which is correct. So this warning is a right warning, basically. Is using Webpack reports. For me, is using the implementation log, because I have full license. Those are the part that I will teach also in maybe in 2 weeks or 3 weeks from now, which is the timing. Whereas Slack, you know, rising time, setup time, hold time, propagation time, and so on. There is no routing issues. See, here they can define to you what signals haven't been routed. You know what does routing mean? That means connecting them from point to point. There are no user-specific timing constraints. Yeah, we didn't put any timing constraints as well. Yes, now we finished. It's a time to program. It's a time to program our FPGA with what? With the output of this, which is called what? Bit stream. Bit stream. Extension of it is .bit. Okay, how can we find it? We're gonna say open hardware manager. Okay. Then we say open target. It might not find it. It might find it. Okay. If it's not finding, we have to define the driver. It found it because I used it before. Okay. See, it found the chip name. Can you see it? ECE7800T, whatever, right? Okay. Hello.
Yeah.
Then I say here, program device. See, this is the extension of the bit stream. See, it's fa.bit. You can find it inside the folders. You don't need to use Vivado. You can actually poke it inside the thing using different way, but you know, I'm not gonna teach it for you now. Here, see, you're gonna under week two, under runs, whatever, .fa. If we're gonna add a logic analyzer inside the chip, that's another lecture I will teach. It will give you another link is DRBT, which is basically debug props file. Okay. Now we are looking, everybody will look to the Vivado and look to my board. Everybody look to Vivado and my board. Okay. Pay attention. Everybody see what I'm doing, right? Program. See, light went off in the board. Why? Because we programmed the board. We programmed the board that, you know, there is 3 switches and 2 LEDs. The only thing in the board will be acting with this full adder. Do you guys agree?
Yes.
Yes.
So the switches, it was, if you remember, one, then, you know, one, it came us to give LED 1, right? Then the other one is not active. That the other one is active. That means, you know, the carry out came and there is no sum. Then, you know, this one is not active, but then, you know, after that it will be active. So what happened when the 3 of them went up, the carry out and the sum, both of them are what?
R1.
Exactly. So now the board is what? I realized what we have in the test bench. So at least today, we run something from A to Z. This is basically what you're gonna do the whole entire semester, but with different circuit, not just FA. Okay? Sounds
Yeah,
good?
sounds good.
Okay, perfect. Now we're gonna go back to my slides so we can get more knowledge that we can use later on and even, you know, for the rest of the lecture. Everybody can see my screen again, right? Okay. So this one I'm gonna pass because I already discussed this with you, right? Delay, we already talked about the delay, right? Like this, 10, right? We did it in the test bench. Do you guys remember that? If you would like to add another delay, 20, 40, whatever. Okay.
Professor,
So this, yes,
and the delay is always in nanoseconds?
yes.
Okay.
Unless you will make a constant in something else and you will put it here. Like, you know, something, and then you define a constant, and the constant here, you can change the values.
Okay, got it.
That later on I will show to you also, right?
All right, thank you.
The slides I made, it's mosquito soup. That means, you know, it can be test bench, it can be RTL, it can be whatever, right? But, you know, the example I show it to you, the FA, you can consider it like a Bible. Like, you know, this is the exactly steps we have to follow while we are working with any task. Okay. Anyway, delay, we already work with it. And then, you know, here, example of instantiation. So I built with you guys a full adder, right? This example is using half adders, right? You can see that, right? So in front of you, there is one here is U1 and U2 and U2. And then, you know, end of the day is bringing you the carry out and the sum, right? And here is the module. Here is the module. It's called full adder. And here is the set of input and output ports. And here's are the internal wires that will be connecting between of the two instantiated half adder. So it's identical half adder, but he called it with different names. For us, we call it what? Comp1. You guys remember?
Yes.
But we call it in this bench. This guy called it an RTL. So I'm gonna show it to you also. If you noticed, the guy used two different ways of instantiation. One based on the order of the list of input and output. And one, it doesn't matter what is the order. The one I show it to you in the Vivado, it was without order. You can, with this dot and the name of the thing and the parentheses, luxury, you can put them in any different way, you know? You don't need to put them exactly like as they sorted in the FA itself. Make sense?
Yes.
Super. Here, something we're gonna use, and it's good to look into it so I can start showing it to you. It's called parameter. Parameter. So there are two different types of defining a parameter to make your design generic. In the circuit we built as a full adder, we didn't need any parameters. You know why? It's just full adder, right? But what about if I would like to build from this full adder, 8-bit full adder? You have to bring a full adder, nearby full adder, nearby full adder. Then somebody else will tell you, you know what? You know, David, make it 16 full adder. Then, you know, if you go ahead and open the file and start sorting them by your hand, it will not be efficient. Do you agree? So there is a way for you to make it parameterized. So you will open the file, you change a parameter to make it 16, then it will be 16. You change the parameter to be 8, then it will be 8-bit. Change the parameter to be 4, it will be 4-bit, and so on. So there are two different types of defining a parameter. One is called parameter, and one is called local param. So the parameter, it can be overwritten in instantiation. Again, so I made a module, right? And I took it in another file and I instantiated, like when I instantiated full adder, do you remember? Then if you change the value of the parameter in the original file in the instantiation, it will be overwritten. That's called parameter. But if you use local param in the original file and you go into the instantiated environment and you change it, it will not be overwritten. Does it make any sense?
Yeah.
For the rest of you guys, does it make any sense?
Yeah, it does.
How are we gonna define a parameters based on the Verilog 2001 style? So imagine here is my module, and here is the name of my module. Then the second line will be what the parameter, as you can see. Then you can start to put your input and output and whatever. Okay. Then end module. We're gonna do it now. So once I finish this part, I will jump there and I start doing it with you. Also, in the test bench, if you remember, I was using the decimal and I was using with you the binary, if you remember, and there is other representation, right? Like octal, hexadecimal, whatever, right? So if I would like it to be hexa, right? I know it's 8-bit, it can be 2 characters. So that's why NF, like this, 2 characters. I would like, for instance, I have 16-bit, I would like to write them in hexa. So 16, H, and then, there are 4, right? A, B, C, D. There are 4 because, here's 4, 4, 4, 4, 16. That makes sense?
Yes.
In octal 8, right? Octal is 3-bit. So if I have a 9 octal, so it's gonna be what? 6, 5, 4. Because this is 3-bit, 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 so it's 9. Right?
Right.
For decimal, is basically D. Sorry. For instance, like this, D16s, that means what? 16-bit wide. So the number in D should be representing something in 16-bit. Sounds good?
Yeah.
There is something also, everybody knows, something is called signed and unsigned. Do you guys remember?
Yes.
So that means we can merge between the type of the data and whether signed or unsigned. See? So basically here I signed or unsigned. Then I put here the format, which is hex. Then I put the value. That means that the last bit in F is representing the sign. Do you guys agree?
Yes.
The last bit in F.
Yeah, in here, right? The last bit here.
Yeah.
In that case, it was FA. So that last bit is basically sign, negative.
Got it.
16-bit, right? Okay, now there is something is called legal or legal if you use what negative numbers, right? So legal, if you would like to write 8-bit holding a negative value, right? So that means here is 8-bit and in a decimal is 3 and is negative. You are not eligible to do anything else than that. So the signed number of bits, that thing will be represented. This is not correct. It will be considered an error. Okay. Also, if you would like to make a separation, if you have a long line of number of bits, you can do it with underscore. So for instance, here, I have a 32-bit and I would like to break them into parts, right? So I can make here 2 digits and then separation, 2 digit separation, 2 digit separation, 2 digit separation within 32-bit. Make sense? Now, same thing, everybody know that, any wire or input can be 0, it can be 1, it can be X, it can be Z. You guys know that? So it can be value 0 or 1, or I don't care, or open floating in error. Like, it's not connected to anything. They call it Z or high impedance. So 0 and 1 normally gonna be like greenish, like in a waveform. Okay. While X is gonna be what? Don't care. So the don't care normally in the waveform look red. And the Z, it looks like blue. Okay. For instance here, right? I have 1 bit and is high impedance. If I look into the waveform, it will be Z. We're gonna do all of this in the couple of minutes, but I just would like to show it to you. Okay. Now the arithmetic operation. So what we can do, we can stop here for the arithmetic operation, and we will go back to visit. We'll go back to visit what? To visit the parameters benefiting from whatever we built from the full adder. Do you guys agree?
Yes.
Okay, now we're gonna go back to screen and say yes. Okay. Here, boom. Okay, now everybody can see my value, right?
Yes.
Okay, so you can close this because this is the implementation. I don't care that much about the implementation anymore. Now we need to build a full adder, but full adder multi-bits. So in that case, we can, here we can say add source, create. And in this case, we're gonna add what? Full adder in bits. Okay. Here, the CN is CN, right? So gonna be what? Full adder in bits, right? CN. How many bits of this? If you have a multi-input full adder, so how many bits for the CN? Hello? Hello?
Sorry, can you repeat that?
Okay. When you build a multi-bit, like 4 bits full adder, the carry input of that 4 bit, how many bits? Let me see, somebody wrote something in the text. Gosh. 1 bit, correct? So they're gonna be 1 bit. Now the port A, right? So if A in bits, and they're gonna be what? Let's make it something now. Okay, just make it 4. Okay. Then you know here if A in bits port B, and that will be here. Let's make it 4 also. The output is gonna be if A in bits sum out. And the guys will be, they're gonna be input or output?
Output.
Hello?
Output. Output.
Can you guys hear me?
Yeah.
I will hear you.
Yeah, I take off this thing. I think it need to be charged. It's annoying me. Anyway, so they're gonna be output and they're gonna be 4 bit also, right? I mean 5 bit. Then we're gonna make another one here, which is basically we say if A in bits, and they're gonna be port sum, and they're gonna be if A in bits, right? Port carry out, and that will be how many bits? Normal carry out for multi bits is what? Huh?
Just 1.
1 bit, exactly. That guy will be our what? Top module. Okay. So we're gonna open it. I will let you guys do all the time whatever I mentioned here, right? You can adding stuff, right? So if you remember, we're gonna do what? We're gonna define the parameter, right? And that's gonna be what? Data width is equal 4. And there we can come and say here gonna be what? Data width -1. That meaning gonna be 4. 3 to 0, basically. 3 to 0. Okay. Sounds good. Now we need to do to make it as one of you guys actually said. How are we gonna make it generic? It's just sorting blocks by blocks is not a right thing. Do you guys agree? So for instance, we can sort now and see what is the consequence, and after that we can fix it, right? So that full adder is multiple full adders, right? So in that case, I have to instantiate who? Huh? This one, right? Into the n bits. Do you guys agree?
Yes.
Okay, instantiate it. So that means, you know, remove the module. We're gonna call it what? Unit 0, for instance, right? Then, you know, we're gonna remove those guys to be what? If you remember, dot, right? Dot. Then we're gonna remove this guy to be what? Another dot. Then we can remove this guy and to be another dot. Then, you know, we do what? Correct? In our case, let's make this instead of 4, make it 2. So it will be easy for me now. Okay. So 2, that means how many full adder we will need? How many full adder we need?
4.
2. So in that case, I need to what? Instantiate it twice. Do you guys agree? And here we're gonna be what? Unit what? 1. We can use the same one. Right? Now it's just a matter of connectivity. Do you agree?
Yeah.
Okay. So connecting, huh? First of all, data BNCN, it will go here, right? You can draw it, you know, in front of you. Or you can even look in Google, you will find, right? Then the AB is this one, right? So A is gonna go here, A is gonna go here, right? B is going to be here, B is going to be here, right? Sum is going to be here, sum is going to be here. But it's not going like that. There are 2 bits, right? I mean, there are data width -1 is basically 2, right? So in that case, we are talking about what? We are calling bit out of array or bus, right? So in that case is what? Everybody see what I have done?
Yes.
So I took the first bit of A and first bit of B, I add them together to bring the first bit of sum. The second bit of B, right? Going with the second bit of A, and they're bringing what?
Sum.
Correct? Then that carry out is basically here. Right? Now, this one, it has to be what? An wire. Just a wire to connect between the carry out of the first full adder to the carry out or carry input of the second adder, right?
Right.
So we have to define it. So we can call it what? Wire. And that's called what? Bridge. I mean, whatever name, right? Bridge. So now we built 2-bit full adder, right? But the question for you guys, is this flexible? Is this flexible to be changing and benefiting from the parameters?
Yeah, you could just increase the
The data.
parameter and then just
That's
add
not
on.
true. That's not true. The definition of parameter is to make it very flexible. That means no longer putting my hand in the code. Now, to make it 3-bit, I have to go literally by my hand and create the third unit and make a new wire between the second and third, right?
Right.
So it missed the idea of flexibility. Do you guys agree?
Yes.
In this case, we need for generate.
Can you repeat that, please?
We need something is called for generate.
Okay.
So I will show it to you now, and then later on we can even discuss it in details, but I will do it just to show you how it's really fancy, okay? One second. It's a statement, it's called for generate, okay? And it is a very lovely statement. Okay, here. Let me do it in front of you. So in this example, right? We can say here, generate for, okay, I equals 0 to I less than data width -1, I equal I plus 1. Begin. And then, we say what? End generate. So what I did here, what is this? What doesn't like me? Interesting. Generate loop is not defined as a gen var. Wait. Oh, sorry. I have to generate the gen var I. Yes. Okay. You know what is this? I have to build an index, and this index in integer format, right? So this is integer format for this process. Okay. Now, if you noticed, I removed some. I made the first block by itself, right? And then I put the rest here. You know why? Somebody can tell me why? Because I can make a bridge. Look at this, and that's gonna be data width -1 to 0. Then that will be what's 0. You see what I did?
Oh, yeah.
Now I can make this I equal 1. Then here I can come and say that, this is I minus 1. Okay. Then this is I, this is I, this is I, right? Then that will not be the case. That will be removed, and that will be bridge of I. Huh? Did you see what I did?
Yeah.
Why? Let's count, right? I equal 1. So in that case, this block is what? And you remove this one and you just make it unit like this, because automatically the tool will start generating a big number. You know what I mean? And I can make for you this 16, for instance. You will see something now fancy. You know what? I'll show you. I said 16, right? If you click here, you will find what? Huh? It made the instantiation for how many? Somebody tell me, how many?
16 times.
No, that's 14.
Oh,
So basically, I have to remove this -1. And that will be 15 times +1, it's going to be 16. So I'll show you. 15 to 1, and this one 16 to 16, right? So if I go now and I change this to be 8, right? Save. What happened? It became this plus 1 to 7, that means 8. So if we study it very carefully, here if it's I equal 1, right? So that means, 1 minus 1 is equal what? 0, right? So basically this is 0, right? Which is correct, right? And then, the carry out, it will be 1. Right. Then that 1 will go here to the second, third, fourth, fifth, sixth, seventh, eighth, until we will reach into the data width -1. Data width -1, it will be data width here. And then, the data width here, it will be our official what? Carry what? Out. So in that case, you can come and say that assign. Take it like this, and later on I will tell you what is the story. It's gonna be what? Bridge data width. This code in front of you is what? Literally generic. This code in front of you is literally what? Generic. It means that, if I keep changing the value of 8, it will be completely changed. The thing that I mentioned in front of you in the slides, I said you can use here local param, if you remember, right? Yeah. Or I can remove the local param to be but parameter. Right?
Right.
Okay. Now, let's make a test bench that will benefit from what we are doing. So in the test bench, we're going to instantiate this block. Do you guys agree?
Yeah.
Since I have a parameter, I can instantiate anything else I want. Why I need to run 8-bit? I can make it 4-bit, and if it works, it works. Right? Then I have to change a little parameter inside, then I'm done. So we still have 8 minutes, so maybe you can catch the test bench. So here, create simulation, create, and then we can call it what? FA in bits, right? Test bench, right? Let's call it TB, so it will be easy for you to figure it out. Finish. There, we don't need anything that much, but I will show you a trick. There, that will be our new test bench. So it's better for you to what? To consider it the new test bench set as a top, right? And here we can make a new parameters. Look at this. We can make a new parameters. And we can call it like this, parameter equal, no parameter, right? Data width, right? TB equal whatever I want, right? Whatever number, right? Then I go there and I just instantiate who? Who I'm gonna instantiate this time? This one. Right?
Right.
Then you go into that one and you start instantiating by removing this. And in this parameter thing, you're gonna remove it to be what? Dot. And you remove this. and remove this. And that will be a value like that. I'll fix it too. But anyway, then we need a name for it, right? So it's gonna be FATB in bits, for instance, right? Leave it for now. There is some errors. I will fix it. That will be here. Dot. That will be here. Dot. That will be here. Dot. That will be there. Dot. That will be another dot, right? And the new test bench will be the value I have here. Okay. 1 second. So far, so good. Any question? Hello.
Nope, no question.
Okay, just give me a second. So here it's gonna be what? Like this. Okay, now it should be perfectly fine. See, now it's perfectly fine. So we can have here many parameters in this area. See, this area can define many parameters. Of course, we need here to have what? If you remember the parentheses, right? So parentheses, parentheses, and parentheses, and parentheses, and then, you know, parentheses. Okay, now we're gonna just put our what? Input output so we can control it, right? So if you remember, any inputs for us is what? Register in the test bench, right? So it's gonna be reg, and it's gonna be data.
I think we lost him.
Huh? Hello?
I think you cut out.
Already? I'm sorry. It's TB, and if a in bits port B TB, right? And those are the input ports. And then, you know, we need the CN, right? So gonna be rig, and that's actually what's a single bit, right? In bits CN TB. And then the output will be what? A wire, right? So gonna be wire, and then, you know, in bits port some TB, right? And another Y, which is gonna be a single bit FA in bits port C out TB. And we are done with all the definitions. So if you want, we can just connect them, and then, you know, next time we can write the code associated to it. Or you guys have time so I can run the test bench. Which way you prefer?
Next time.
Everybody in favor for next time?
Yeah.
Yeah, that's fine.
Okay. Anyway, being slow, I don't know why, but anyway. Here. Initial, begin, end, right? And there is here finish, and that will be our what? TST bench. Okay.
Okay.
Okay. Okay. So it's, I think so far, you know, to summarize what we have done, we talked today about, you know, a practical way to study the Vivado, the connectivity between Vivado and, you know, from the RTL perspective and simulation perspective, following by the constraints and how we can connect the constraints into the RTL after it will be tested, followed by some definition into the language using the Git level capabilities that we have to build a bigger circuit by concatenating instantiated components or modules, and then benefiting from the parameters that is completely different than local parameters. If you look very carefully, the parameters in the V, it was 8, and then we came into 4. That means we can overwrite it, and the overwritten here help us to look into the test bench. If you look very carefully, if you go there, you will find that we already have a 4 units, even though there we have 8 units. So the parameter overwritten. And we look into how can we make it completely flexible and generic using generate for loop with genvar to define the indexing inside the for loop. If you have any questions, please let me know. If you have any concern, also please let me know. A copy of this code, a copy of the recorded video will be posted on the Canvas under modules week number 2. Thanks so much. And I think you already have a copy of the slides. We haven't finished it yet from the last week. Any questions? Anything, is not clear?
Professor, do you mind?
I cannot hear you. Hello? 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 Hello?